Uh, Good evening, folks. Tonight I'd like to show you a linear optimization problem. And this is one we've been tackling, or similar to some that we've been tackling in class the last couple of days for my grade 11s. And this question says, a painter has exactly 32 units of yellow dye and 54 units of green dye, and he wants to mix as many gallons as possible of color A and color B. Each gallon of color A requires 4 units of the yellow and 1 unit of the green, and each gallon of color B requires 1 unit of yellow and 6 units of green. So like a lot of these optimization problems, one of the most difficult things is figuring out where my equations come from and where they start. So in this particular question, we have a painter who's trying to max out the number of gallons of paint he can make, but he's limited because he only has so many units of yellow and so many units of green. Right. So the first thing I'm going to do is I'm going to just set up some parameters, and I'm going to say let X be color A, and I'm going to let Y be color B. Because I'm going to end up graphing these, and as I graph them, X and Y tend to work really well, because those are the variables we're familiar with. So if we've got A requires 4 units of yellow and 1 unit of green, and B requires 1 unit of yellow and 6 units of green. Setting this up in like a matrix or a grid is a good way to just sort of establish myself. I know that A needs 4 yellow and 1 green, and that with yellow, I need to have 4 and 1 and 1 and 6 for green. All right, so, my objective function. One of the main problems of these is I have to create objective functions, which are functions for my final solution. In this particular one, my objective function is to max out, and my objective is to make as many color A and color B as possible. So if X is color A and Y is color B, then my objective function is, I use G for gallon, X comma Y, X plus Y. So it's just the sum of the number of color A that he can make plus B. Simple as that. Or X plus Y. My constraints are a little bit more difficult. So what are my constraints? Well, the first constraint or the boundary that I can set up is I have to have at least 0 color A and I have to have at least 0 color B. So I'm going to say that X has to be at least 0 or bigger, greater than or equal to 0, and the same with Y. Y has to be greater than or equal to 0. Now I have constraints on the amount of yellow dye that I can, or yellow paint using the yellow dye that I can make, or there's a constraint on the green dye. My yellow is constrained in that I'm going to use, for every A I make or every X, I'm going to use 4, and for every Y or color B, I'm going to use 1, but I can only ever use as many as 32. So I could say that 4X plus Y has to be smaller than or equal to 32. For my green, I have 1 for X, or for color A, and I have 6 for B. So my my fourth constraint would be X, 1X plus 6Y has to be less than or equal to 54, because I only have 54 units of green dye. So now that I've got these 4 constraints, what I'm going to do is I'm going to take all 4 of them and I'm going to put them on a graph. So X plus Y is less than or equal to 54. That graphs very nicely here, represented by the red line. And these lines keep going indefinitely. I just made it smaller so it was a little easier to see. And then we have 4X plus Y is less than or equal to 32. When I graph that out, it's represented by the blue line. My other 2 constraints, X is bigger than or equal to 0, and Y is equal to 0. Those are actually defined by my axes, but I have them here. I've done them in black, but you can't really tell the difference versus the regular axis. All right, so now I have to figure out my feasible region. Once I know my feasible region, so I'm going to use this test point right here, 5 and 5. I'm pretty sure that because this is less than and less than, and this is greater than and greater than, it's going to be lower than the red line, left of the blue line. So it should be somewhere in here. I pick 5 and 5 because it's just easy numbers. I test it out. 5 plus 6 times 5 is smaller than or equal to 54. 35 is 6 times 5 is 30 plus 5 is 35. Yep, that's smaller than 30 and 54. And I'm going to come over here and it says 4X plus Y. I'm going to use the 0.5 and 5 again. 4 times 5 plus 5. Yeah, this is looking like it's going to be work. It's under 32. So 20. 20 plus 5 is 25. Yep, that's smaller. So this test point shows me that my feasible region is right here. and that means it's lower than these lines. It's to the right or above the axis, and I could color that in. And let's see if I can color that in nicely here. There you go. Color it in with that nice yellow-green, since that's the colors we're sort of talking about. So this is my feasible region. Now, why is that important? Well, on the perimeter of my feasible region, I am going to find intersection points. My intersection points are 0 and 0, which is where x and y meet, 8 and 0, which is right here, 0 and 9, which happens to be the y-intercept of the red line, and where the blue and the red line cross, they make an intersection point very nicely at 6 and 8. So that means I have 4 points that I'm going to test using my original optimization function. So I go back to my objective or optimization function, and I am going to say that g of x comma y is equal to x plus y. And I'm trying to max out the amount of paint I can make. So I'm going to take all 4 of these points that I was able to pull from my graph on the feasible region, or the extremes of my feasible region, 0 and 0, 0 and 9, 8 and 0, and 6 and 8. Where did I get those points? It's those points that touch on the feasible region and are right here. So 6 and 8, 8 and 0, 0 and 0, and 0 and 9. And I'm going to plug each of those points into this function, x plus y. So 0 plus 0 is equal to, well, equal to 0. Then 0 plus 9 is 9, 8 plus 0 is 8, and 6 plus 8 is 14. Since we're trying to max out our paint, this is our max. Therefore, we can say that the painter can make 6 gallons of paint A and 8 gallons of paint B. That is his max. He can't make any more than that. This is, the numbers here are pretty simple. It can get a little tougher, but that's an optimization function. Good luck. If you're one of my grade 11 students, you will have a comp check or an ICA on this on Thursday.